to either continue in chemical equilibrium. Today is a big day. Big. Let me explain. So as we look back at the do now, know of course the date. I should take note here, point 3. So today, we'll look at KC and how some equilibrium problems if we look condition. Significance of that statement. Well, in order to calculate K or equilibrium concentration pressure, whether it be, we must use or take it at equilibrium. So the last lesson we saw we chart, and today we saw that in our use of a chart, if we were given any of any reactant, we were given then able to determine the equilibrium of all other substances, determining the change in that and using moles to determine the change in the other reactants or products, which leads to determine the equilibrium values and all, which would then lend itself okay. Only going to be given an addition. So the question is, how are we going to determine having use of quadration? Oh no! Here, visualizing this over this particular day that I've done all 2 years of teaching. The equation are actually quite comical. For some reason, it's like I'm on a death threat or something. I feel about it after we do this. But anyway, I'm assuming that you've all used the quadratic equation in your advanced algebra class by now. But if you've forgotten how to do it, I'm going to show you the more significant quadratic is that it has a variable purpose. A lot of times quadratic and this, but had it really, focus what it does. We're going to go through. Okay, let me get rid of that and bring our notes. And there they are. And so this was actually example 3 was the problem we did in our last lesson where we first learned how to use an ice chart. So hopefully we're good with that. And so now I'm just going to advance this up to today's lesson. There we go. Okay. So if only the initial concentrations of all the reactants and products and the value of K, in this case Kc, are known, then the equilibrium concentrations can be calculated only by using a specific method. All right? We're going to set up an ice chart just like we did last time and use the stoichiometry or mole ratios of the reaction along with an unknown variable X to establish the changes in concentrations, and then use those to establish an expression for the equilibrium concentrations. Again, this also applies to P and pressure. So think about when you use the quadratic equation in math, math and you're solving for x, right? Well, that's exactly what we're going to do here, only then we are going to have x assigned as a variable for a specific thing within our equilibrium calculation, which then will allow us to calculate the equilibrium values of everything, and ultimately k. So let's go on to the next here. So solving for x will involve the use of the quadratic equation. Familiar to you. Where x equals negative b plus or minus the square root of b squared minus all over 2. Of course, is in reference to a general setup of a quadratic equation, which is ax squared plus b, plus bx plus c equals 0. And we're going to be using that here. So the solutions of x, here's where we get into why this is so useful for us. One of the solutions, because remember, in solving quadratic, you're going to get two answers for x, because this is plus or minus. Okay. One of the solutions of x will yield either a negative or an unreasonable concentration or pressure, if we're doing Kp, for reactants, which is chemically meaningful or actually impossible. That type of solution is rejected, and the other one is our true answer. Okay. All right, so let's take this example and we go through it in painstaking detail, because I want to make sure that you understand fully how to do this. So we have here a liter glass, and this volume that is filled with 2 moles of H2. This is moles now, and 4 moles of I2 at 448 Celsius. The Kc at this temperature is at 0.5. So Kc is given, and it is necessary. All right, by the way. What are concentrations of H2, I2, and H2 at equilibrium? All right. Okay, so first things first, remember in an ice chart, you can only place 2 types of values, all right? Either a molarity, if we're dealing with concentration, or a pressure, masses. So moles and volume or mass, we talked about this the other day, those cannot be used in an ice chart, and so we're going, but we have an information here to get molar concentration or molarity. So remember real quick that N equals V, and so for hydrogen, and this is initially, all right, so our initial hydrogen concentration would be E2 N equals N over V, which is 2.00 moles over 2.00 liters, which is 1.00 molar. And then initially for iodine, our concentration, again, N equals N over V, would be 4.00 moles. Again, our volume's 2.00 liters, 2.00 molar. So those are going to be the initial concentrations of our reactants. All right. So I will put that here for hydrogen, here for iodine, and hopefully by now, after yesterday's lesson or our last lesson, you already know what the initial concentration of our product is. And I'm listening, and I just heard it. It is 0. Right? Initially, whatever is placed in the reaction, we're talking about before the reaction commences. Well, any products then would be 0. All right. So last lesson, we were given one of these equilibrium concentrations, as I mentioned a few minutes ago, which allowed us to then determine the change in the concentration for one of the reactants or products, and then based on mole ratio, we could then determine the change for the other reactants or products, which then allows us to then determine the equilibrium values for everything, which is then used to determine K. Well, here we're given a K. That's it. This is all we got, right? One thing we do know is that reactants disappear and products appear. That we do know. Now, how much does it change? How much do any of them change? We don't know. But what we're going to utilize there instead of a value is what we always use in math when we're trying to determine an unknown value, and that is X. All right. So as I look at the mole ratios here, and again, I had already balanced this equation for you. These are 1 to 1 and 2. All right. So this is going to decrease by some value. Again, we don't know what that value is. So I'm just going to place an X there, and it is a molarity. Same thing with I2. All right. It is also going to decrease by some unknown value. And the mole coefficient number for I2 is also 1. So this would also be minus X. So technically it's 1X. All right. That mole number coefficient is 1. But again, we don't need to use that. So we'll just get rid of that. Okay. Now be careful when we do this one. So we know this is increasing. The change in the concentration of HI is increasing. And here's the other thing we know. It is increasing at twice the rate that these two are decreasing, because the mole number here is 2. All right. So it's increasing not by X, but it's increasing by 2X. Okay. And then down here, just like we did the other day, we're just going to do what it says to do. 1.00 minus X. Well, that's what we got. So we have 1.00 minus X molar. Here we have 2.00 minus X molar. And then over here, 0 plus 2X molar is, of course, 2X molar. So we don't have any equilibrium values, but we have an expression that relates those values to each other based on mole ratio. So we're good, all right? So now let's get the ball rolling on solving. First of all, we want to set up our K expression. This is Kc. Again, these are concentrations, so we're using Kc. So Kc would be equal to, remember, it's the ratio of products to reactants. So we have HI, concentration squared, because of that 2, over the concentration of hydrogen times the concentration of iodine. So there is our Kc expression. Now we're going to plug in. Remember, when solving for K, you have to have equilibrium values. Well, we don't have values, but we certainly have an expression that relates those values. So Kc is given at 50.5. HI is 2X. Now, be careful here. It's not 2X squared, it's 2X the quantity squared, which are two very different things, all right? So make sure you catch that. Over 1.00 minus X times 2.00 minus X. Well, I think I see now, as I'm visualizing this, some of your eyebrows raising. You're thinking, oh, here's where the quadratic is going to appear here in a little while. And you would be absolutely correct in assuming that. Okay, so I guess first things first, I am going to cross multiply this thing and get an expression here. All right. So basically, if I cross multiply this, I have 50.5 times this quantity. So what I'm going to do is go ahead and FOIL this thing out, all right, and get an expression for these two quantities multiplied together. In doing that, I'm going to go ahead, for simplicity's sake, because I can, eliminate the 0.00 there, just make it a little easier as we do the math. But remembering, of course, that those are going to play into our sig figs and our final answer. So anyway, 1 times 2 is 2, right? 1 times 2 is 2. Now we do the inside outside. Negative 2 times x is negative 2x, and negative x times 1 is negative 1x, and negative 2x and negative 1x added together are negative 3x. So we need to get your FOIL method back to the forefront of your brain today. And then, of course, the last one, negative x times negative is positive x squared. All right. So basically, I'm cross multiplying this. And at the same time, I went ahead and FOILed this out. So this times this we have right here, and then the other side is 2x, the quantity squared, is 4x squared, times 1, of course, is 4x squared. So that's where we're at so far. All right. So now I'm going to go ahead and distribute this 50.5. All right. But I think before I do that, I want to put this thing in the proper format. All right. Remember, we said in using the quadratic, we want it to look in this order here. So I'm just going to go ahead. You could do it in your head, and do that and skip this particular step. I'm just going to show you, so you can keep track of where we're at. So 50.5 times the quantity x squared minus 3x plus 2 equals 4x squared. Again, you could probably skip that step, but I wanted you to see it. Now I'm going to distribute the 50.5. So we have 50.5 x squared minus 151.5x. I'm just distributing the 50.5 all the way through, plus 50.5 times 2, which is 101, equals 4x squared. Last thing I'm going to do before we get ready to hit the ground running with the quadratic is to get this thing in this format right here. So I'm going to subtract 4x squared from both sides. We have 46.5 squared minus 51.5x plus 101 equals 0. And now we are ready to roll on the quadratic equation. Okay? So remember, x equals negative b plus or minus square root b squared minus 4ac all over 2a. Okay? So I'm going to go up here now. So I have x equals negative b would be, well, b is negative 151, so that would be positive now. 151.5 plus or minus the square root of negative b squared. So negative 151.5 squared minus 4. A is 46.5 and C is 101. That's all under the square root sign, all over 2a, which is 2 times 46.5. Okay? Now at this point, I'm sure with your fancy calculators, you could do all this in one fell swoop, and that is fine. However, I'm going to do it out long ways. Hey, back when I did this, we didn't even have a calculator. So it was a little different animal back then. So I'm going to go ahead and do it the old-fashioned way. Again, with your calculator, you could probably do this all at once. But I'm going to do it the long way because I want to make sure that when you do try this on your calculator, you get the correct answers. And if you didn't, you plugged something in the wrong way. So anyway, so X then comes out to be 151.5 plus or minus. So when I did all this in here and took the square root of that, this all inside here was actually 4,166.25, square root of all that. When I squared that, subtracted all that out, I got 4166.25. And so into getting the square root of that, and I'm not rounding yet by any means, 64.54649487 all over 93. So this is going to give us two answers, 151.5 plus 64 blah 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 divided by 93, and then our other answer would be 151.5 minus 64 blah 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 divided by 93. And so I'm going to do that. These are going to be our two final answers. So now I'm going to go back to sig figs, which of course then would be 3. All right. So what I get is X equals 2.32, and remember this is a molarity, or X equals 0.935 molar. So just like in math, when you use the quadratic, you're going to get two answers. Okay. Now the question is, of course, in math, when you get your two answers, that's it. Here, different story. All right, so here is where the usefulness of understanding the quadratic formula comes into play in regards to equilibrium. So we have two answers. One of those answers is, to be honest, ridiculous. All right, and one is correct. How do you know which is which? Well, take your answers and look back up here at your ice chart. Think about it. I'll start with 2.32 molar. If I put in 2.32 molar here for X, what's my equilibrium concentration of hydrogen going to be? Well, it's going to be 1 minus 2.32, which is negative 1.32 molar. Think about that. Come on, people. It's impossible. A negative molarity? I don't think so. The lowest concentration of a solid you can have is 0, meaning there's no particles of solute in the solution. And so that's impossible. Or if you take 2 minus 2.32, you still get a negative concentration, which again is impossible. Either one. So that's out. That's out. Here's your answer right here. Right there. All right. So, based on that, the question is, what are the equilibrium concentrations of all of 3 substances? And now we're ready to say that. So, let's see. I guess I'll do it over here. Hopefully you can still see. So, the equilibrium hydrogen concentration is equal to, well, right here it is, 1.00 minus X. 1.00 minus 0.935, and this is 2 decimals, this is 3, so we're subtracting now, so we're going to have to round to 2 decimals. So this would be 0.07 molar. Okay? Our equilibrium iodine concentration. This is 2.00 minus X. Again, X is 0.935. Here again, 2 decimals, 3 decimals. Our answer must have 2 decimals, 1.07 molar. And our equilibrium hydrogen iodide concentration is 2X. So 2 times 0.935. So this one is 3 sig figs. We're multiplying by a constant. And so our answer needs to have 3 sig figs. So these two answers were given by decimal places. this last one by sig figs equals 1.87 molar. And there, my friends, are your equilibrium concentrations. Okay? So, here is where knowing how to use an ice chart and knowing what mole ratios, how they affect the change in the concentrations or pressures, if we're doing KP, within that reaction based on those mole ratios becomes vitally important when determining an expression for our equilibrium values, which we don't know what they are, but we can come up with an expression for them based on those mole ratios, and then ultimately use the quadratic formula to then help us to find x. And again, one last time, remember that the quadratic formula is going to give you two answers for your potential answer. However, one of us is going to be, again, ridiculous, and the other one is not. Now there is a possibility, let's say, and this is definite possibility, that your two answers, one of them was negative and one is positive. Well, that's an easy one. You don't even have to look back at the chart. If you get an answer that's a negative molarity or a negative pressure, if you're doing KP, that one's out. Okay? So it's pretty easy to evaluate which of your two answers is correct. Either by, again, if one's negative, that's automatically out. Or if they're both positive, go back up to your ice chart and check in there. Okay? Okay, so that's the lesson on the ice chart and quadratic formula. So you should now be able to do, if I'm not mistaken, the assignment is equilibrium number 3. And so that would be assignment attached to this lesson. And again, be careful in doing the quadratic formula. This lesson, this one sticks out above almost all others for the entire year. And that students frustrated with this assignment or with this procedure simply because they make simple mistakes when inputting the data in their calculator, or they make simple mistakes in this procedure right here, in particularly with foiling. Okay, foiling foils them. So hopefully that will not happen to you. All right. So be very careful and meticulous as you work your way through this process. It'll save you a lot of headaches. So until next time, when we meet again to continue on with Unit 12.2, this is Mr. Keister signing off. Take care, everyone, and we'll talk to you next time. All right. Here we are. See you later, guys.